What if you could predict a student's GPA based on behaviors of past students in the hopes to make meaningful impact on the academic future of your incoming cohort? In this walkthrough, we'll build a linear regression model to do just that. We'll show how it works, interpret the results, and even simulate what happens when you change student characteristics, and, most notably, hit all things regression equation. Now let's quickly tune back to what is a regression before we transition to what is a regression equation. So a regression, a linear regression especially, is something that helps us predict the value of a continuous outcome. So in our case here, we have first year GPA, and we're using a combination of predictors like ACT scores, demographics, student behaviors, academic preparedness, what have you. And what it's going to do is it's creating an equation, which we consider like a mathematical recipe that combines each variable in order to make a prediction for our outcome, which is first year GPA. Now moving to a regression equation itself. So an equation is simply just a math sentence that predicts an outcome, like GPA here, based on a set of input variables. So it looks like this. So this is the formal variation of what it looks like in more or less Greek and Roman notation. So the predicted GPA equals beta naught plus beta 1 times x1 plus beta 2 times x2, and on down the line depending on the number of variables you have and incorporated, which in this case we're going to use 14. So what beta naught is the actual intercept. So that is the constant that you're going to get in the regression equation. And then beta I, so beta 1, beta 2 is the slope of the predictor for the xi. And the output is the predicted value of your dependent variable, which in this case is GPA. So why it matters specifically. So a regression model isn't just a test of significance like other hypothesis testing inference type models. It's an actual forecast engine. It's a means to plug in inputs to generate a value, and in this case GPA, to figure out what levers we can pull to make sure that we're optimizing or maximizing our outcomes. So it lets us simulate what might happen if a student gets tutoring, chooses a major versus being undecided, or works on campus, lives on campus, what have you. And ultimately what it becomes is a tool for intervention, something we can use in a meaningful way to enhance the academic experience and hopefully the academic success of our students. Now, before we get into the regression equation and the interpretation and the simulated output, let's actually walk through in SPSS in a familiar fashion how we actually run the regression so that we can have proper interpretation of our output on the back end. The first thing I'm going to do here is introduce our data. So this is from a series of videos that I built called A Dozen Methods, One Data Set, which was a walkthrough of how to use a method map decision tree and the way in which you best select a method given the question or problem you're working with and the structure of your data you have. So it's the same data set that I'm going to use here for our example. This is a set from a 4-year college. And the goal here was to try to predict the first year GPA, and then from there, predict the probability that a student would be on probation in the spring. So these are the two core variables we're working with. In addition, we have 4 ACT math scores that range from 1 to 36. Binary variable about whether or not a student was decided or undecided about their major. A binary variable for male, female. Age, which is a continuous variable ranging from 17, I believe, to upwards in the 20s. In-state residency, so 1 for in-state, 0 for out-of-state. Legacy status, whether or not somebody in the family was a graduate of the institution, so 1 for legacy, 0 non-legacy. Binary here. Campus living status, 1 for living on campus, 0 for not. Whether or not the student is employed by the school, 1 for yes, 0 for not. 1 for using tutoring and 0 for not. Same for supplemental instruction, which is an academic category. 1 for using it, 0 for otherwise. And then whether or not a student is associated with a fraternity or sorority, 1 for Greek, 0 for not. So we're going to go ahead and go to analyze. We're going to go to regression, linear. And I already have these blocked in here. So first year GPA is our target, is a continuous variable. So this is the right fit. We have a series of continuous and binary or categorical variables that we're using. All of these are actually binary, so it's not going to split up in multiple categories. So like, for instance, if that was major and there were 5 or 6 different majors, it would read this completely differently than looking at it in a binary. And when I get to the actual regression equation and how to use it, we'll see what that means. So we've got Our five components here that are academic preparedness is what I'm essentially calling this. Demographics, male, age, and state residency, whether or not there's legacy status, living on campus by itself, employed by the school, and then three academic factors using tutoring, attending SI, and Greek affiliated. And that's all. So now how we saw the actual output achieved. This is what our model looks like from the form of an equation. So taking predicted GPA as our outcome, you see 1.226 is our constant, and then all of the coefficients corresponding to what they multiply into based on either whether it's a categorical variable or a binary, one for calculating into it. So this is probably the more difficult way to look at it. If we take it in a more easy to digest format, this actually helps us look to the math itself, which I'll get to here in a second. But there's two things to really keep to the core of interpretation. So first, what we do with a continuous variable. So in the equation form, you've got a beta I times xi, where xi is a number with some meaningful numerical scale. So take ACT on a scale of 1 to 36. That's a numerical scale rather than something that's binary, yes, no, male, female. And then with each 1 unit increase in that xi leads to a bi change in the predicted outcome. So for example, let's say your coefficient here for BI is 0.052 for that math score, which is your XI. We would say that every 1 point increase in ACT math predicts a 0.052 increase in GPA, holding all other variables constant. Now to the binary interpretation, it looks similar, but the input is different. So the equation would be BI times DI, where DI is 0 or 1. So 1 would be yes and 0 for no, or 1 could be yes, male, where 0 is female in that binary form. So how it works, if the value is 0, the term drops out. So there's no effect on the prediction. It just adds to 0. And then the rest of the equation takes care of itself. But if the value is 1, the coefficient is simply applied. So for example, the coefficient here of minus 0.190 for an undecided major would say if the student is undecided, which is that 1, the GPA is predicted to be 0.190 lower than students who have a declared major. If not undecided, so if they have a declared major, 0, the term contributes 0 to the prediction itself. Let's take a series of interpretations here. So first looking at ACT math. So ACT math, every 1 point increase predicts a 0.052 increase in GPA, holding all else constant. And then a binary variable with undecided major, which we just discussed. Being undecided is associated with a 0.190 lower GPA, hence the negative coefficient. Male, also a negative coefficient. So being male predicts a 0.455 point decrease in GPA compared to females on average. Age being a continuous variable, so this also being a negative coefficient would suggest that every 1 year increase in age predicts a 0.029 decrease in GPA. And then finally, looking at a positive binary coefficient. So for 1 equals yes, attended SI, students who attended supplemental instruction are predicted to have a 0.381 higher GPA. That's how we interpret these. So then let's run a simulation. So we have what we had in that equation, and ultimately what we say is we have student A out of all those features that we got out of this equation here. This is what nets out to actually create the math. And so you've got the constant and then all of their values given what the index was for, and then that net student nets out to be a 3.85. So now we're going to get to an actual simulation here from here on out. So now I want to give you an example of how to take that actual equation and then plug in the variables so that you can actually estimate the GPA points. So we just saw in the example of student A over here, these are the representatives. So ACT math score 26, English 25, reading 24, science 26. So those are the performances on academic preparedness. Undecided is coded as 0, which would mean no, not undecided. Male 0, so that would mean female. Age 18, so that's continuous variable. In-state residency 1, so that would suggest in-state. Legacy status 0, so not legacy. Living on campus housing 1, so that would be on campus housing. Employed by the school 1, so employed by the school. Use tutoring as a 1, so that would suggest use tutoring. Attended supplemental instruction, suggest attended SI, and Greek affiliated not. So what this shows you is how to actually take on this side what the variables in their respective categories are, and then how it's actually coded in the data so that you can use it for regression. So coming back over to the equation, what we have is the beta coefficients, right? And that, so these are unstandardized. So this is, again, the real world look at when you plug in the actual variables, this is what's going to come out. So what I've done is with the math, I've carried over the score. So like, let's take student A that we just saw in the example that ended up with a 3.85 GPA. What I'm going to do is I'm going to take those values, and then you can actually see how dropping in those values actually calculated the GPA based on the regression equation. So what it's doing is it's taking that variable, each of these, 26 for those continuous variables all the way down to 26 for science. And then what it's doing is it's actually calculating against the beta coefficient. So it gives you the value of that ends up being an additive function that gets into the estimated GPA. So that's how the equation actually works. Note too that you have to use the constant. So that's essentially your base, your starting point, your beta not point. So this gives you an idea of what a student with, the mid-level ACTs with a decided major, that's female, age 18, is an in-state resident, not a legacy, lives on campus, employed by the school, used tutoring and SI, and is not Greek affiliated, ends up predicting to a GPA of 3.85. Let's look at a different student though. Okay, so let's take a look at student B that has the same ACT scores. So academic preparedness is the same. What's going to be different though is the undecided major. We're going to say they're an undecided major. They're a male. They're out of state. They're a legacy, and then they're not living on campus. And they did not use tutoring, and they did not use SI. So those are the core differences. So quite a number of differences here. So let's see what this student populates out to be. As you see, male being a pretty significant factor here with a p-value well below 0.05. We know that's going to have a significant value. We're also going to see using supplemental instruction being a significant value. So just based on not using SI and being a male, we're probably going to guess that that's going to add up to at least a point in difference. And then when we drop it in, we see that in fact it is. That predicted GPA of a male student of this type with this kind of blend would be a 2.8. So now from here, we can kind of just play around and see, like, this becomes a simulator. Like what would the outcome be if all of a sudden this was a decided major? Bam, you're at a 3.0. If I'm a female, I'm now at a 3.45. So it shows where the real differences are here. If I'm an in-state resident, what does that do? Only, a tenth of a point, or a little more than that. But you can see how that coefficient converts to that as well. If you found this helpful, hit subscribe, grab the data set from the link below, and try it out for yourself. Stay curious out there.